Hello and welcome back to Differential Equations. We are going to take a look at the second part of our lecture on 5.2, which involves the eigenvalue and eigenvector problem. And this one is going to now we're going to take a look at the complex values as well. So we'll do another example. We'll do the complex values. We'll see what else we missed last time. So we did the definition. We did example for distinct real eigenvalues. And I think we are good. Yeah. So we should talk about complex eigenvalues. I'm not sure why is it showing. Trying to figure out if this is all good. It's showing the calculus 2. Is this correct? Give me 1 second. Oh, okay, it's good. I follow the chat on a separate screen, and then I think I accidentally clicked one of the yesterday's lectures and I thought it didn't switch in YouTube and so on. It's all good. All right, so we can just start and deal with today's concepts. So, eigenvalues and eigenvectors can be real or can be complex. It depends on what we have in our equations. So when we have the real eigenvalues and the real eigenvectors, we get those eigenpairs which would give us the E solution by what we are used to. And I did 2x2 and 3x3 example last time. Now we want to take a look at complex eigenvalues. And that would pretty much work the same. So we can want to follow the notation in the book. Generally, we denote our complex numbers as z equals a plus bi, right? That's in general. But now they want us to say, since it's a eigenvalue, they want us to put a lambda, and they are using p and q. Now, since eigenvalues travel in pairs, creating what we know as eigenpair, then we have a lambda bar is equal to p minus qi, and I'm going to get rid of the original notation. I'm going to put the blue box around this, and I say these are your complex eigenvalues. That's what they're going to look like. And the complex conjugates will leave us with, because the matrices are real, right? So A and I are real matrices. So no, you don't have any of the complex values in them. That means that A conjugate is the same as A and I conjugate is the same as I. Those are the two things that we need to know. So conjugating a real matrix, because there is no part that changes sign, matrices stay the same. But the conjugate that matrix stays the same. Good. So what we are going to have is now we're going to have a vector v, which is our eigenvector, and that one is going to be complex. That's the only thing that can be complex in the whole thing. I mean, other than I did not write the form. I should have written that you have lambda I v equal to 0 vector, and now you can conjugate these, which is, it's a vector at the same time, so it's getting a little bit busy with these, with the notation, right? So vector v, a plus a1 b1 I, a2 b2 I, an plus bn I. So it's a column vector with complex numbers. Please just look at the complex number as just a regular number. It has two dimensions, real and imaginary, and it's kind of really sad that we call it imaginary, because there's nothing imaginary about imaginary numbers. Square root of -1 is equal to I. I guess for the lack of creativity to come up with a name when this thing was discovered 300 plus years ago, 350 years ago, I think for the lack of creativity to name it, they call it a complex number and then use the imaginary word in it. But this is nothing magical or imaginary or something. They are as real as number 7 and number 9, because we use them to create alternating currents, and that they're used in sciences, and it is not something that, look, we can flex in mathematics. These things are used, and you don't see number 7 walking down the street. You also don't see 2 plus I walking down the street. It's the same concept. This is just a two-dimensional number. And we also have hyperdimensional numbers today, which is more than 2 dimensions that we have in a complex number. So there is nothing complex about it. There is nothing complex, and also there's nothing imaginary about it. Just whole concept has a very unfortunate names that stuck for more than 300 years, and we are stuck with it. But try not to grasp those terms. All right, so this can be decomposed, guys, to a real vector A plus a real vector B times I, which creates a vector of complex values. See that? So it's a very simple transformation. We use the property of linearity, right, to come up with this. Now, this means that we can conjugate vector v, and the conjugate of the vector v would be a minus b I. So the solution, the associated, right, the problem would be x of t is equal to ve lambda t, where we have our complex number. That's a lambda, that doesn't have that. And we can write that as, we use the p plus qi times t. Vector v we just broke down into a plus bi as vectors, and then e to the pqi t. And remember that we are breaking apart the complex e, right? The complex e that we know from before breaks down with the cosines from the sine and cosine, if you remember, right? So this part, maybe I should use a different color here. There we go. There, this peanut over here. That peanut is going to be the good old cosine, and now we're using qt plus I sine qt, and we know that we can deal with that in different with a different notation. So x of t is going to be given by as e to the pt, a, which is the a vector, cosine qt minus b vector sine q t plus I e to the pt times the same b cosine qt, and that's a vector, right, plus a sine qt. So we actually have over here, if you take a look, right, this, we call it real. As I said, unfortunate words. Real, call this imaginary, and we can come up with the x1 solution and x2 solution for the real part of x of t, which is the first part, and x2 is the imaginary part. There we go. So, depending on, I'm going to now erase these guys because I use them just to explain where this guy is coming from, and I'm going to box these. So, actually what I can do is I can write in blue x of t is equal to x1 plus x2i. How about that? And I forgot these arrows on all of this. All of the x's. Because those are all vectors. Remember, you can have as many of these. Is it a minus or a plus for the imaginary part? Minus or plus for the imaginary part? You mean this one? If you mean this one, yeah, it's a plus. I think I have everything, because that's the conjugate, that's the original, that's the yeah. This should be 100% good. For the x2, that's x2. It's a plus. Oh, yes, sorry, right here. Yes, I copy. Yes, for the x2, it's supposed to be a plus. Good eyes. Thank you. All right, so this was just the part. Yes, next the example. So this is the part of just deriving what, if you want to call it, the formula is, but when you follow calculation, all of this just falls out of the calculation. So complex eigenvalues will deal with the complex, will yield the complex vectors, and then the complex vectors, right, will be put into the solution that will be a complex solution, and then it's either in E, right, the exponential form, or you break it down into the trig form with the cosines and sines. So let's take a look at the mess over here and see what we get. So remember, our differential equation will look no different, right? It will have all real values, something like x1 prime is equal to 4x1 minus 3x2, and x2 prime will be given as 3x1 plus 4x2. So this is just a standard, this is example. So this is just a standard differential equation. If you change, one of these numbers, you can make it into a real. So there is no difference there. So once I have this, I immediately get my matrix A, which is 4, -3, 3, and 4. So that will be my matrix. Then I have the determinant of A minus lambda I, which is going to be, we subtract lambdas on diagonal. So I have 4 minus lambda, and then -3, and then 3, and then 4 minus lambda. And I do the determinant. So this is going to be 4 minus lambda squared plus 9. Needs to be equal to 0. So 4 minus lambda squared, that's going to give me 16 minus 8 lambda plus lambda squared plus 9 is going to be lambda squared minus 8 lambda plus, this is 25, I guess. 25 equal to 0. Then we are going to crank the quadratic formula on this. We have negative b, that's 8, plus minus square root of 64 minus 4 times, and then I have 25 times 1, divided by 2 times a, which is just 2. This is 8 plus minus square root of, and this is 64 minus 100, which is negative 36, divided by 2. This is 8 plus minus 6i over 2. We get our lambda 1 to be the complex number 4 plus 3i, and the lambda 2 to be the complex conjugate of it. They always have to end up being complex conjugates of each other. There is no around it, right? It's just that's what it is. So we have our complex lambdas, and now we're supposed to go and work out the equation for if you remember A and B, to obtain our eigenvector, which is what we did yesterday, or not yesterday, 2 days ago, with real numbers. I just hope you practice those, because now these ones will look weird, right? We are using the same equation. It's just that it's a complex calculation now. So now we have a matrix. So now we have the bracket, right? We had the absolute value straight lines up there because we needed determinant. Now we need a matrix, which is 4 minus lambda, so 4 minus 4 plus 3i, and then we have negative 3, and then we have 3, and then we have 4 minus 4 plus 3i. And that matrix needs to be multiplied by A and B, and needs to give us 0, 0. So this is our standard calculation for so use lambda 1 there, and we have now what is this? 4 minus 4 is 0, so we get negative 3i, and then minus 3, and then 3, and then 3i, and then A and B, and that gives us 0, 0. So 4 minus 4 is 0, and then you have negative 3i, and 4 minus 4 is 0, and you get... No, that's also negative 3i. That's also negative 3i. Yeah, negative 3i. Okay, because the negative distributes, right? So 4 minus 4, and then we have a negative 3i. Those of you struggling with complex values, subtraction and so on, think of this as 4 plus 0i minus 4 plus 3i. And then say, let me do like terms. So like terms would be 4 minus 4, which is 0, and then like terms would be 0 minus 3i, which is minus 3i. If you're having issues with complex numbers, subtraction and addition, that's literally what you do. You're doing like real with real and imaginary with imaginary, right? So this is what we get. All right. Now going back to our problem, we are going to have here negative 3i a minus 3b equal to 0. So it is row times a column equals this. That's your basic matrix multiplication. And then we are going to have row times the column equals the bottom one. That gives us 3a minus 3ib equals to 0. So we get these two. And now we need to figure out what are the values that would solve this case, right? So I'm going to first divide everywhere by negative 3 and the bottom one divide by 3 to get rid of as much of negative signs and everything, and to clean it up as much as possible. So on top I am getting IA plus B equal to 0. Negative cancels, 3 cancels, I stays, and A stays, and then a negative cancels, 3 cancels, B stays, 0. Okay, good. Now divide the other one. That's A minus IB equals to 0. And now the question is, what eigenvector is going to make this work, right? So remember, we choose the one that has a single. Both of these have a single, but choose any one of them. I'll choose the top one, has a single, and then pick the other one to be 1. So A equals 1. You pick that. You could have said A equals to 173, but why? So A equals 1. And if A is equal to 1, then you will have I plus B equals to 0, from where B equals negative I. Right? That's your calculation. So the vector V that you are looking for is going to be 1 and negative I. It's a complex vector. That's okay. It's a complex vector. So now that you have your vector V, you can check this one in the second equation to see if it works. That's a 1 minus I times negative I. This is 1 minus I plus I squared, and that's 1 minus 1, which is 0, so it works. Right? If you want to do a quick check and make sure that it satisfies, I mean, it has to satisfy both equations if you did calculations correctly, but, you know, it's good to check. So now I have an eigenvalue, lambda, which was 4 plus 3i, and I have an eigenvector v, which is 1 and negative I. And what is the solution now, which corresponds to our x equals e to the, v e to the lambda t, right? Well, that's clearly, right, that's the solution, so it's clearly 1 negative I e to the 4 plus 3i t. Now I'm going to box the exponential solution here, but the issue with this exponential solution is that it contains i's. And if the solution contains I in it, it's not a real, using terrible terms, but we have to, it's not a real solution, right? And we want a real solution. So we have to switch this one back to, sines and cosines. So how do we do that switch, right? So if I have my complex vector here, I know that I use the e part to write the sines and cosines. So far I have x bar equals 2, and I have my 1 and negative I over here, and then I have this e to the 4t that should be known from chapter 3, is the same, right? When you have e to the complex. This is new. This is old. Be careful, right? That's old. The new part is just having this vector in front. So what I have here now is e to the 4t, and then I have my cosine of, should I write the c? Nah. So I have a cosine of 3t minus I sine 3t plus I sine et. Okay, so that is our formula. If you guys remember the formula, at one point we had, not sure where we talked about it. At one point when we talked about complex values, I would have to go and rummage through a couple of these lectures. We said that e to the, I guess, omega t or whatever it was cosine omega t plus I sine omega t. or maybe it was something else other than omega. So I am using that, and then that could be multiplied by e to the, I guess, a, right? In that case would be e to the a t, and now these would add into a plus wi. Oh, there's supposed to be an I here. Oops. I, everything times t. So that's how you decompose this, right? You decompose it into the real part and the imaginary part. So now we just follow through with calculation and we're done. Just follow through with calculation. We have 1 times all of this mess, and then negative I times all of this mess. And then we just pick them off one by one, right? So e to the 4t, you can factor out, well, it's already a factor. Just put that one out. And then run I through all of the terms, right? 1 times cosine 3t plus I sine 3t. And then times negative I is negative I cosine 3t. And then plus sine 3t. Because, why is a plus sine 3t? Because negative I times negative I, negative I times positive I is negative I squared, and negative I squared is negative 1, so that turns into a positive 1. So that's why there is a coefficient of plus 1 over here. I have to be a little bit careful about that. And that gives us our 2 vector solution, right, where we pick off the x1 and x2. So we have the first one plus the second one. So e to the 4t, I'll write them first as vectors, as cosine 3t minus I cosine 3t. And then, oh, I should have, I see something is wrong because they were supposed to see that now swap, because the complex number is a plus bi, right? I goes the second spot. So I have to write this one more time. Kill me now. E to the 4t. We'll have to do one more example of this mess. Cosine 3t plus I sine 3t. And then you have your sine 3t minus I cosine 3t. All right, so that was just to swap that row. And now I have 2 column vectors. So I have e to the 4t cosine 3t sine 3t plus e to the 4t, put I, you can kick I in front, and you have over here sine 3t and negative cosine 3t. So you can break these guys apart, and now you can see your solutions x1 and x2. They are given in these vectors, this one and this one. So those 2 vectors are going to give you your x1 and x2. So this is x of t, which is the solution to the whole problem. So this is going to be cx1 plus c2x2, right? And in our case, we just have these guys, and they will get their c1s and c2s. So we get the these are the real, right, the real parts that we are using for the solution. Aha, okay. I see the question in chat. Let me just write this out, and then I'll get to it. So I have now C1 for the cosine 3t and sine 3t. and then plus C2 plus C2 sine 3t and minus C2 cosine 3t. So this is one sort of the solution. And if you want to have them separately, then there will be x1 of t is e to the 4t c1 cosine 3t plus c2 sine 3t. Mike, I see your question. I will right there. E to the 4t c1 sine 3t minus c2 cosine 3t. So we have these two solutions. Ta-da! Isn't there another lambda to worry about? No, there isn't. Because when you are dealing with complex conjugate lambdas, both of them give you the same answer at the end. So you only need to solve one, and the other one is paired up, and they give you already the solution for both. So when you have a real lambdas, you have to go and do right calculation for each lambda separately, come up with their single, right, unique eigenvectors, and then put them all together in their proper terms and all of that stuff. For complex pairs of lambdas, you only need to calculate one. That's all you need to calculate, just one. And it will give you both solutions, because in the complex, when you do the when you come up with a complex solution here, it gives you the real part of the solution, it gives you the imaginary part of the solution, but when you pick off the vectors from in there, there are two real ones, and those are the solutions that are already linearly independent. And you can see they're linearly independent because this would work as minus cosine squared minus sine squared, factor out -1, sine squared plus cosine squared is equal to 1, and the solution in the Wronskian would be -1, which is different than 0. Solutions are linearly independent. So it already works out as two of them together. So now you get to wave with this in front of others and say, look what I learned in my elementary differential equations course. Woo! Let's just see some more of this mess. If you have systems that contain 3 equations, right? You can have systems that contain 3 equations, systems that contain 4 equations. It just makes this longer and more painful to calculate. So it just takes a longer time, because now your determinant is going to have the 3 things to worry about. So you will have to come up with right. But remember, you cannot have a lambda that is for the 3 equations. You can't have 3 complex lambdas. You can have 2 complex lambdas because they could create a complex conjugate pair, and then a single real lambda, which is the regular eigenvector from before. So you have to be very careful about that. So there will be a calculation for calculating a vector of lambda. I'm kind of dreading to go through the 3x3 case. I mean, it's something that is because it's long to calculate. We're not going to put it on a test, but the trick is that you should see at least one of them, I guess. I just don't want to do it. Coefficient matrix can be found in inspection and factoring. Apply the eigenvalue method. Yeah, so these are the ones that have the 3. Maybe I should. How about we do another one or two with initial condition and call it quits. The other one is just gonna take an hour for no reason. You do have. Let me see. You do have an example in the book. Yeah. If you go on the book on page 291, example 4 has. Yeah. 2-page calculation, and you know they skip steps in the book, so that's just gonna take an hour. But it's done over there, and you have x1, x2, x3 solutions at the end. I'm going to do another 2x2 case, which you absolutely must know, and I'm going to do this one with initial conditions as well. So we just need to be a little bit careful. Find one with initial conditions. Here, problem 6 is fine. We have x1 prime is equal to 9x1 plus 5x2, and x2 prime is equal to negative 6x1 minus 2x2, with initial conditions given x1 of 0 is 1 and x2 of 0 is 0. So these are our values. So now I'm going to create the matrix A as we always do. So matrix A, matrix has the brackets. That's 9, 5, negative 6, negative 2. Then we are going to create our, to calculate our lambdas, we're going to do the determinant of 9 minus lambda and 5 and negative 6 and negative 2 minus lambda. Oops. And determinant of that needs to be equal to 0. So we have our 9 minus lambda, and I'll give you the trick over here. I'll say 2 plus lambda and put a minus in front, and then plus 30 equal to 0. And the reason why I did that is so I can FOIL this faster. So now this is 9 times 2 is 18, so I have negative 18, and then 9 minus 2 is 7, so plus 7 lambda, because you would have 9 lambda minus 2 lambda, and then you have minus lambda squared, and we still have plus 30. So now when we get rid of the parenthesis, we get our lambda squared minus 7 lambda, and then minus 18 and 30 is plus 12 equal to 0. And good. Yeah, minus 7 lambda. It is minus 7 lambda. And that's what we have. Alright, so now we have 7 plus minus square root of 49 minus, yes, that's going to be 49 minus, wait, well, this is not complex. This is not complex. Oh, because 5-2 is not for complex only. 5-2 is for both. It's gonna take time now to figure out which example is complex here. This is 7 plus minus 1 over 2. So we're getting 8 over 2 is 4, and 6 over, we're getting 3 and 4 as lambdas. These are real. So where can I cry now? I have 16 problems, and only 4 of them have initial conditions. So lambda 1 is 4, lambda 2 is 3, not complex. So just, this is old stuff. Okay, let's try. I guess problem 11 is the last one of the bunch that has the initial conditions. So, yeah, we did 2 examples of this yesterday. Let's see if this one works better. I'm just going to fly through this to get to hopefully complex part faster. This is familiar. Is this the example we did yesterday? No, it's not. Okay. Let's see. So I have my matrix A, which is 1, negative 2, 2, and 1. I have my determinant 1 minus lambda minus 2, 2, 1 minus lambda. That is going to give me 1 minus lambda squared plus 4. That needs to be 0. When you square this, it's 1 minus 2 lambda plus lambda squared plus 4 is going to give me a 5 over here equal to 0. And now that's going to be negative b plus minus square root of b squared is 4 minus 4ac, 20, there is the complex one, over 2 equal to, good. All right, so this is the complex one. Yes, you can finish the complex. Yes, you can finish the previous one as a practice. Yes, definitely. You want to call it home? I mean, it's in the book. It's a homework anyway. So yeah, sure. All right. So what we have here is the complex. So we have lambda 1 is going to be given as, well, actually let's solve this a little bit more. This is equal to 2 plus minus square root of negative 16 over 2. And that's a negative 4, so 2 plus minus 4i over 2. So we have our lambda to be given. See, I'm not going to put lambda 1, lambda 2. I'm going to put lambda and then lambda conjugate, and they give us the same values. So this is 2 plus 4, so that's 1 plus 2i. And lambda conjugate is 1 minus 2i. Now we only need 1 lambda from the conjugate pair to crank the whole procedure over here. So all I'm going to do now is plug this into the matrix up there to come up with the matrix that needs to be multiplied into a and b's for the vector. So I have 1 minus, and I'll put 1 plus 2i in here, and then we have negative 2, and then we have 2, and then we have 1 minus 1 plus 2i, and then we have that times ab, and that's the vector, well, you can call it the zero vector or zero matrix, whatever. So now I have 1 minus 1, so that's going to give me negative 2i, and then I have negative 2, and then I have a 2, and then negative 2i, times AB gives us 0, 0. So negative 2ia minus 2b equal to 0, row times column. And 2i minus 2ib equals to 0. Remember that I divided the top one by negative 2, divided the bottom one by 2. Last time was a 3, whatever. Just to get these numbers out of the, let's make it easier. So ia plus b equal to 0, and a minus ib equal to 0. So that's our system. Pick one with a single, you can pick either one now. So if you pick, it's gonna pick again the top one, doesn't really matter. So this one, we say a equals 1, so you pick that. So you pick one that has a single, and then you choose the other variable to set it to be 1. Because you don't want to set b equal to 1 in the first equation. If you set b equal to 1 in the first equation, then your a is going to be 1 over I, negative 1 over I, then you have to rationalize and you know, do that work. So you pick 1 with I to be 1, and then you have your b to be negative I. Because, well, actually, let's just write it. So this becomes now I plus b equals 0, from where b is negative I. There we go. Beautiful. So that takes care of this situation, and I get my vector v, which has 1 and negative I. Is this the same vector we had earlier? Yeah. So now the solution is going to look exactly the same. Such is life. So our x bar solution is vector v times e to the lambda t. Vector v is 1 and negative I, and e is, our lambda was 1 plus 2i. Times t. So that was our solution, and we can break this apart. You know that this part over here is broken, right? So we have 1 negative I, and this is going to be e to the t, right? Because it's a 1 over here, right? And this part on the other side is going to be cosine, in our case, of 2t, right? Cosine of 2t plus I sine 2t. So that's our complex over there. And now we have this part to simplify, and then this part simplifies. Terrible the way I circled it, but such is life. So x bar of t, vector, not bar, vector. We're going to have e to the t, and I'm going to keep them separate. Cosine 2t and minus I cosine 2t. So that's when I multiply these guys. And then I'm going to have plus IE to the t, and have this as I sine 2t, and why did I? Oh yeah, that's that I. This I is out. Sorry, this I is out right here. That I stays out in front of E. So this is now 1 times sine and negative I times sine 2t. Now we distribute this I into there. So it's going to be e to the t cosine 2t negative I cosine 2t plus e to the t, and when I distribute this I inside, it becomes I sine 2t. I times I is negative 1, so this becomes sine 2t. There we go. So now we put these together into the single x of t, where we are going to have e to the t outside, and then we put these guys in order. So that's cosine 2t plus I sine 2t, and then I write sine 2t first, minus I cosine 2t, So now we have complex values inside. Now look at the coefficients. It's again like in the chapter 3, you have a coefficient of 1 in there because that was in your, now lambda used to be r, right? Real part was 1, so it's 1 times t, and the imaginary part was 2, so all of your sines and cosines have 2's inside. And now we have this part that will be with C1, and this part that will be with C2. So x of t is going to be e to the t to write the solution, right? And we're going to put C1 cosine 2t, C1 sine 2t, then we have plus C2 sine 2t and minus C2 cosine 2t when we just pick off the real parts, just like for the other one. And that's it. That's it. If you want to write them separately, you can. This is in the vector form, right? Or you can write them in, I don't know what you will call it, exploded form. I don't know. x1 of t as e to the t c1 cosine 2t plus c2 sine 2t, and the x2 of t, these are not vectors now, these are just solutions, e to the t c1 sine 2t minus c2 cosine 2t. All right, cool. Are we done? Of course not. Why would we be done if we have initial conditions, right? So initial conditions were x1, what was that? x1 0 0 0 4. Okay. So x1 of 0 was 0, x2 of 0 was 4. So we can plug in 0 of 0. So the first equation would say 0 is equal to 1, and then we have C1 plus 0, because e to the t, e to the 0 is 1, cosine of 0 is 1, so C1, and sine of 0 is 0, kills C2. So from here we calculated that C1 is equal to 0. The other one is 4 is equal to 1, and then C1 is a 0, and you have negative C2, from where C2 is equal to negative 4, right? So look, C1 died, that kills these completely in the solution. So my x1 solution is e to the t, and then a c2, that's a negative 4, so that goes in front, and then sine 2t, and the x2 solution is going to be e to the t c1 is 0, that dies, and a c2 will give us a cosine, so negative 4 cosine 4 e to the t cosine 2t. Yay! There they are. Again, this used to be called x of t, and this used to be called y of t, right? Two separate ones. Yep. So nothing that's a couple of hours of careful and diligent work, right? Can't figure out and sort out. Plus 4 2 for x2. Plus 4 2 for, yes. C2, yeah. As I make the mistake telling you, be careful. Yeah, be careful. And then I I mess up 2 or 3 times per problem. Wow. That's a lot of calculations right there. And you are going to see this again in your 300, 400 level courses. This is coming back. Let me just check in the book. They have an example somewhere. Oh, perfect. If you go to the page 286 in the textbook, you are going to see a link of three tanks that gives you the rates of gallons per minute, the way you're filling those tanks. And I'm just gonna say hello chemistry. Okay, hello chemistry people, because chemistry people in this case, right, when you do the mixtures of different kinds of liquids and then they're dripping, right, there was you will have to, this is the way it's modeled. Hello mechanical engineers, when you have 2 or 3 or 4 of these mechanical systems that are oscillating, and this is still homogeneous system, so they're just oscillating around. And hello electrical engineering, obviously, where you have loops with inductors and resistors, multiple loops. So all of these things put together. Now, clearly electrical engineering will run into this case way more than anyone else, because the whole alternating realm rests on the cube roots of -1, and the cube root of -1 has a -1 as a real answer, and then 2 complex roots that you can calculate as -1/2 plus minus root 3 over 2i. You can go and calculate those on your own. So the whole alternating currents realm of electrical engineering. We did not have any allo. I'm talking about the design side, not about the user side. The design side is the one where you actually have to compute all of these things to make sure that the tanks are big enough and that they have appropriate, and then you push it to the workers who are following directions. Make this drip this fast. If it's dripping faster than this, then stuff will go bad. So it's one thing to be engineer, and it's completely other thing to be the worker. So yes, Phil, what you wrote there is 100% correct, but for the worker's perspective, those that are designing the systems, right? So that's the part that question is, what are you going for? Are you going for to be a designer, an engineer, or you're going for to be a worker who understands that you're not supposed to open the valve past a certain point? So that's going to be the difference between knowing this stuff and not knowing this stuff. You get to work either way. It's just the question is, what is actually your job, right? What is actually your job? Yeah, I am not going to go into 5.3 today, because this is enough, and you can enjoy your weekend with figuring out the complex values and 5.2 in general, because it is a very lengthy and calculation intensive section. I am going to open my office hours tonight to the students that are having exams tonight, so my pre-calcs and my pre-calculus and calculus courses will be joining me tonight, possibly, for office hours. Their exams are this weekend, and I will see all of you guys next week. If you have anything that we need to discuss, we will discuss it on Monday, and then or shoot me an email. When is your next exam? So the next exam will contain chapters 4, 5, and I think so. Your next exam, I'm thinking. Let me just check the dates one more time. Our final exam week. So I think our final is going to be on the weekend of 8 and 9 and so on. So we can have our next exam, somewhere in 20s, maybe even 30 or a first or a second. So it is not going to be next week. Definitely not next week for the next exam. So we are going to have our regular 3 classes of instruction next week, Monday, Wednesday, and Friday. And then going into the week of April, Monday of April 27th, we will see somewhere in that week whether we want to do it earlier or later for the weekend, and then next weekend to have the final. The semester ends on either, I think, 12th or whatever, something like that. Semester ends. I was hoping they will add another week for us, but they are not. Or we can push the final exam for the literally last we can. I think we need to end by 12th, because 18th, Monday 18th, we can, Monday 18th is when the summer 2 begins. Can I send my work from last exam? I think you emailed and I emailed back that, you can send the stuff. Or maybe there was someone else. What do you mean, Cole, if you need to study? I'm hoping you're working minimum 2 hours every day on differential equations, including Saturday and Sunday, 7 days a week. This stuff is insane. I mean, if you're learning this for the test, you are absolutely doomed when you transfer out. Exam grades are completely irrelevant. If you don't know this, courses when you transfer out will be absolutely impossible. I have to contact some of my students to send me regular homework assignments for any of the courses, like, just to see that this is, I mean, if you are not going to be in STEM, then you don't need this stuff. This is basic elementary course. This is literally 1 + 1 = 2 when you go this stuff. The entire course is 1 + 1 = 2 when you go on to your 300 and 400 level courses. Learning this for the grade has nothing to do. You gotta be doing this every day because it's fun and it's awesome and it's actually elementary and needed. So I hope that the exam situation is, Oh, I see. Okay, so you're doing extra exam. Okay, good. You scared me there, man. Good. All right, perfect. So just keep working on this. Keep following stuff. The homework is already open for you guys on MyMathLab, and we will have this one. We're still having the project. Well, I was giving it a thought about the project, and being that we are not getting our week back and so on, I was thinking to do something special with the project. I just have to make sure that it would actually work out. So the project that it was in terms of the old is not there. So there will be no project. There will be no project the way it was. The grade for the project will be added to the homework. I was planning on creating a special final exam review homework or a lab or something, and call that like a course survey or whatever. I haven't finalized this yet. I'm already doing this in 2 of my other courses. For pre-calculus 1 and calculus 2, they have labs, And because we are not having labs now because of the situation, I transformed their labs into a course survey thing, but they have the lab and the project and the homework. So I had to redistribute everything. Now for you guys, the project that I was supposed to assign 3 weeks ago, which was supposed to be application of the stuff that it's important, right? Because 90% of the course is garbage calculations. And only 10% is application that it's actually important for life, which is word problems, right? So the project was supposed to be 3 or 4 applied problems that you crank differential equations for, create an awesome presentation in terms of paper, right? And then hand that in. I've been doing that for 8 years now, and some great results with that. But we can't have that anymore because we don't have time. Second, you don't get to hand in the paper copy. Electronic copies are garbage, obviously, because you don't have to worry about having it nice and clean and not crumbled and stuff, because it was a part of the grade as well. So we are not going to have the project in its glory and usefulness as it was in the past because of the stupid virus situation. So I might convert the project again into the survey, where you are again going to get on my MATLAB from every section, right, one problem from every section we covered. And then that's going to serve as the course survey, is going to serve as a course review for the final. So it's going to be like a final exam prep and everything in one, and it's also going to be the grade. So, I mean, practically you did all of the problems in my MATLAB already for homework and so on. So this might be another, instead of the project. So that's an idea. I have to figure out what to do with that. Yet I'm still debating and trying to get input. Had a very good department meeting yesterday. I learned a lot of great and useful information. See what the consensus of other professors was. So I should have all of this. I'm thinking about it. So I already solved the 2 classes, and I still have to solve the stuff in my head for another 3, which is my algebras and you guys. But I think that I'm pretty much going to do the same for you guys, what I did for calc and pre-calc, and just convert that project. So we'll see. All right, go study, do 10,000 examples, and I'm going to go back to grading your exams. Sid, send the stuff if you haven't in the email. I don't care which email. You can do Canvas, you can do the regular email. If you haven't sent that stuff in, I can't remember if I graded your exam or not. But I will take a look, and those that did not send the work obviously will not have partial credit. I will just have the grade plus the quizzes. Those that did send the work, again, it's taking me forever, so I'm hoping to have all of this done by Monday. It's taking me forever because I have to redo every problem. You all have different numbers, you all have different functions, so technically every single student has a unique exam, and this has just been a living nightmare for me to grade this exam, this midterm. So I will eventually, I can only do 2 or 3, and then I have to stop, and because it's just technically at that point I did 3 tests and look for partial credit and so on, and I have to look at 3 different locations for information to do just one exam, and it's just way too much. So we'll do much better for the second one, for the second exam, the one that will be in, like, let's say 10 days from now or so. I'm looking to have it on Canvas, and probably if I can't do anything with the Canvas integrated problems, I'm going to do the a file with problems or something like that. So it's just way too insane what happened with my MATLAB. All right, I will see you all Monday. Back to grading. Bye.